Welcome you all in this session of fluid machines. In this lecture, we are going to study about the reaction turbine. Since we have already completed the impulse turbine, that is Pelton wheel turbine, we have solved a numerical problem on Pelton wheel as well. Now we will study the reaction turbine. Please observe what is the meaning of a reaction turbine first of all, and how actually the water enters inside the reaction turbine, and what is the arrangement of the various components of the reaction turbine. Let's start. The water which is coming out from the penstoke enters inside a casing. The water which is coming at the exit of the penstoke firstly enters inside a casing. Inside the casing, there is a set of guide vanes which is mounted over the stator. Please observe, inside the casing, there is a set of guide vanes, and these guide vanes are mounted over a stator. Now, inside the stator, there are the runner vanes or moving vanes which are mounted over a rotor. There are moving vanes inside the stator. There are the moving vanes which are mounted. There are the moving vanes which are mounted over the rotor. Thus, the stator and runner are entirely inside the casing. The runner and the stator are entirely inside the casing, and this casing is full of water at each and every moment. The casing is full of water at each and every moment, and stator and runner are mounted inside the casing itself. Stator has a set of stationary blades which are known as guide vanes, while the runner has a set of moving vanes to obtain the runner power. Now, when the water is working over the vane, when the water is working over the moving vanes, not only the kinetic energy of the water contributes, but the pressure energy of the water also contributes in the runner power. Please observe, when the water enters the moving vanes and leaves the moving vanes, not only the kinetic energy of the water decreases, but the pressure energy of the water also decreases. Therefore, runner power is going to be obtained as a contribution of decrease in the kinetic energy from inlet to the exit of the vane, and because of decrease in the pressure energy from the inlet to the exit of the vane. In impulse turbine, please note that basic difference. In impulse turbine, the pressure remains constant at atmospheric pressure throughout the entire vane. That is, in an impulse turbine, when the water works over the vane, the pressure energy of the water does not contribute. It is the only kinetic energy that contributes in the runner power in case of an impulse turbine, because the pressure remains at atmospheric pressure from inlet to the exit of the vane. But the vanes of the reaction turbine are designed in such a way that when the water is working over the vanes, not only the kinetic energy of the water decreases from inlet to the exit of the vane, but also the pressure energy of the water decreases from inlet to the exit of the vane. Therefore, in a reaction turbine, the runner power is going to be obtained as a result of decrease in the kinetic energy as well as decrease in the pressure energy from inlet to the exit of the vane. Because of decrease in the kinetic energy, we have somewhat known as the impulse action. That's what we saw in impulse turbine. And because of decrease in the pressure energy from inlet to the exit of the vane, there will be a reactive force on the vane, and this effect is known as the reaction effect. And therefore, the turbine is known as impulse reaction turbine. I think it is very much clear to you. Let me again repeat the concept of reaction turbine. Probably I must ask impulse reaction turbine. In impulse reaction turbine, the runner power is going to be obtained as a result of decrease in the kinetic energy of water when the water is working on the vane, and also the pressure energy of the water decreases when the water is working over the vane. So both kinetic energy decreases, pressure energy decreases. As a result of that, two actions are going to be achieved. One is impulse, another one is reaction. Therefore, the turbine is known as impulse reaction turbine. I think it is very much clear to you. So this is the definition of impulse reaction turbine. Please note, impulse turbine, Pelton wheel turbine is an impulse turbine where only kinetic energy contributes, only KE contributes. The pure reaction turbine is one in which only pressure energy contributes. There is no contribution of kinetic energy. Please note, and pure impulse turbine, only kinetic energy contributes. Only kinetic energy of the water contributes. That is, when the water enters the vane, its kinetic energy decreases. As a result of that, a work is obtained or a force is exerted on the vane. In a pure reaction turbine, only pressure energy contributes. But in an impulse reaction turbine, both kinetic energy as well as the pressure energy contributes in the runner power. So this is the definition of a reaction turbine. Now let me give you a diagrammatic representation of a reaction turbine. I am here asking about a radial flow reaction turbine. In most of the reaction turbines, the flow is radial. That is, either the flow is radial inward or the flow is radial outward. Please observe, in most of the reaction turbines, the flow is either radially inward or flow is either radially outward. There are some axial flow reaction turbines as well. They will be dealt later on. Now I would be talking about radial flow reaction turbines. In this lecture, we will talk about radial flow reaction turbines. That is, either the flow is radially inward or the flow is radially outward. So this is a diagram of a radial inward flow reaction turbine, inward flow radial turbine. Please observe. This is the exit of the penstoke. I already talked to you that there is a casing. This is the casing. This is the casing. This is the casing. Inside the casing, there are guide vanes, stationary vanes, which are known as the guide vanes. These are the stationary vanes which are known as the guide vanes, and they are mounted over a stator. Please observe the diagram. These are the stationary vanes. They remain stationary. These stationary vanes are known as guide vanes, and they are mounted over stator. Now there are the moving vanes. These are the moving vanes. Please note, these are the moving vanes. These are mounted over a runner. These are mounted over a rotor, which is known as runner. And this is the shaft of the turbine to which they are attached. Now please observe, the water enters at the exit of the penstoke. The water enters inside the casing. The casing is entirely full of water. Now the water enters radially from all the directions. The water enters circumferentially from all the directions. Once the casing is filled of water, the water enters circumferentially from all the directions. This is the radial inward flow. The guide vanes guide the water like this over the moving vanes. The function of the guide vanes is to guide the water over the moving vanes, and water works over the moving vanes. This is the inlet to the moving vane. This is exit to the moving vane. This is the exit to the moving vane. This is the inlet to the vane. This is exit to the vane. So that is how the water works, or that is how the entry of the water takes place inside a reaction turbine. This I have given you for a radial flow reaction turbine because the flow is in radial inward direction. Please note that this is the entry of the water inside the vane. This is the exit of water at the vane. So the water is flowing radially inward in this particular diagram. So there are four important components of the reaction turbine. They are the four important components, main parts. If I have to write the main parts of a reaction turbine, then they are: first is the casing. You have noted down, water enters the casing. Once the casing is full of water, guide vanes guide the water toward the moving vanes. Moving vanes or runner vanes, you can say runner vanes, or runner simply. And finally, one more component is there, draft tube at the exit of the turbine, that we will deal with later on. So let us see a cut section of the turbine. Let's observe the cut section of the turbine. This is the casing. Cut section I am going to visualize in this diagram. This is the casing. I am talking about the inward flow turbine. Again, the flow is inward. The radial inward flow is there. So this is the casing. I am showing you a cut section of this. I have cut it down like this, and now I am showing a cut section of this. So this is the casing. These are the guide vanes, casing, guide vanes. Now this is the moving vane. Please observe, this is the moving vanes or runner vane. This is the runner vane mounted over the runner or rotor. The water enters the runner vane at point 1. This is the entry point. The water leaves the vane at exit and then goes like this fashion, in this fashion. So this is the casing, guide vanes, and these are the runner vanes or moving vanes. The water enters circumferentially at point 1, water leaves the vane at point 2, and this is a radial inward flow reaction turbine. Now please, This is the width of the blade at inlet B1. This is the width of the blade at inlet B1. This is the width of the blade at outlet B2. Width of the blade at inlet B1. Width of the blade at outlet B2. Okay. D1 is the diameter of the runner at inlet and D2 is the diameter of runner at exit. Please observe, D1 is the diameter at the inlet, diameter of the runner at inlet, and D2 is the diameter of the runner at exit. Since this is an inward flow reaction turbine or radial inward flow turbine, therefore D1 is more than D2. If it would have been an outward flow reaction turbine, then D1 and D2. D1 would have been that and this would have been D2. So please, inward flow reaction turbine, D1 is more than D2. Because water enters at the larger radius and leaves at the smaller radius from the axis. And B1 and B2 are the width of the blade at inlet and exit. Width of the blade, B is width of the blade. Okay. Now, so I think you are very much comfortable in this reaction turbine, basic components of reaction turbine. Now we have to note an important point over here, which is very important from numerical point of view. Since there is all-round admission of water, there is an all-round admission of water circumferentially. There is an all-round admission of water circumferentially from all the directions. Therefore, if you are going to calculate the area of flow at the inlet, then area of the flow at inlet will be pi d1 b1. You have to assume like this, a ring of height b1 at inlet, a ring of radius of diameter d1, a ring of diameter d1 and of thickness b1. So there is circumferential admission of water. Therefore area of flow at inlet would be pi d1 b1 and area of flow at outlet will be pi d2 b2. Therefore mass flow rate area at the inlet, area of flow at the inlet will be pi d1 is the circumference and b1 is the width. B1 is the width perpendicular to the plane of paper. Pi d1 would be the circumference and b1 would be the thickness or width perpendicular to the plane of paper. Therefore the flow area at the inlet would be pi d1 b1 and the area of flow at the outlet would be pi d2 b2. Hence the mass flow rate can be calculated as rho pi d1 b1 rho a into v, rho pi d1 b1 into vf1, which is equals to rho pi d2 b2 vf2. This is the formula for mass flow rate in reaction turbine. Please observe, we have to use this formula for radial flow reaction turbines. Mass flow rate will be calculated using this formula. Rho av, rho density, area of flow is pi d1 b1 at inlet and vf1 is the velocity of flow at inlet, because in radial direction the velocity of flow is vf. Please note, I will tell you from the velocity triangles that in the radial direction the velocity is vf1. So the mass flow rate will be calculated using this formula. You can use this as well as this, whatever. Okay, I think it is clear to you. Now let me show you the velocity triangles for reaction turbines. We have already talked about these velocity triangles in the previous classes. When there is a radial inward flow, the velocity triangle is somewhat this for radial inward flow. We have already talked about this, please note. And we have work done per second over the vane, work done per second on the runner is given by this formula m dot vw1 u1 plus vw2 u2, because u1 and u2 are now different. Because the radius at which the water enters and leaves are different from the axis of the runner. Therefore this is also known as runner power itself. This is the runner power. Whatever the work has been done on the moving vane, which is known as runner power. So runner power, this is the expression for the runner power in case of reaction turbine. So this is the velocity triangle for a radial inward flow. Please observe, this is inlet, this is the exit, so flow is radial inward. The velocity triangles, I think you are very much comfortable in the velocity triangles. We have already learnt about that, radial inward flow runner. And this is the velocity triangles for radial outward flow runner. The flow is, this is entry point at the smaller radius from the center. This is the exit at R2. This is R1, this is R2. So this is a radial outward flow runner. And you observe that along the radius there is the component of velocity vf1 at inlet, and along the radius r2 the velocity component is vf2. Therefore, I have used in mass flow rate rho pi d1 b1 is the area and vf1 is the flow velocity at inlet, because in radial direction the velocity is vf1 and at exit in the radial direction the velocity is vf2, therefore, and the area is pi d2 b2, therefore it is. So mass flow rate would be calculated using, and this is the runner power itself, this is the runner power, the formula is same, runner power.